All right, here we go.
Hi, I'm Aleksandra from Presentaion High School.
I'm Joshua Heron from Presentaion High School.
And I'm Aleksandra from Presentaion High School.
And our research experiment was on the effects of mass, molarity, and temperature on the temperature change of the reaction between sodium bicarbonate and acetic acid. Some real-world benefits of this research experiment include that it can be used to make cold packs, which can help to relieve pain, serve as muscle relaxers, and they are also used in insulated shipping.
Some background on our topic is molarity, which is the concentration of a solute in a solvent, enthalpy, which is the amount of heat taken in or released by a chemical reaction, and endothermic reactions are reactions that take in more heat than is released. And the system is the chemical reaction that's occurring, and the surroundings is everything around it. And solubility is the property of the solute in a solvent. Our problem is the effect of mass of sodium bicarbonate, molarity of acetic acid, and temperature of acetic acid on the temperature change between the reaction of sodium bicarbonate and acetic acid.
We hypothesized that increasing the temperature of acetic acid to 30 degrees Celsius, increasing the mass of sodium bicarbonate to 7 grams, and increasing the molarity of acetic acid to 1.16 molar will yield the greatest temperature change. This is the setup of our three-factor DOE. Our factors are acetic acid measured in degrees Celsius, sodium bicarbonate measured in grams, and the molarity of acetic acid measured in molars. And these are our low, standard, and high values.
These are some of the materials that were used for this experiment. Here we have pictured acetic acid, sodium bicarbonate, a lab quest attached to a temperature probe, a calorimeter, and a 100 milliliter graduated cylinder. Some other materials such as a scale and an incubator and a refrigerator were used, but they're not pictured here. Our procedures began with making the acetic acid solutions at the high, low, and standard molarities. After the solutions were made, they were stored in their proper locations, such as the refrigerator, incubator, and fume hood. They were left in these areas for a 24-hour period, ensuring that they had a standard initial temperature. After the initial temperature was reached, the sodium bicarbonate was massed out to the high, low, and standard values. After massing out the sodium bicarbonate, the trials were randomized and executed. To execute the trials, as shown here, the acetic acid was poured into the calorimeter. After the acetic acid was poured into the calorimeter, the temperature probe attached to the lab quest was placed in the calorimeter as well. The temperature probe was left in there for 30 seconds to get a read on the initial temperature of the acetic acid. After this 30-second period, sodium bicarbonate was then added into the calorimeter, and the temperature probe began to measure the temperature change of the reaction occurring. As the reaction occurred, the temperature probe was used to stir in the sodium bicarbonate to ensure for a more thorough reaction.
This is our experiment on a more molecular level. The white dots represent the sodium bicarbonate and was poured into the blue acetic acid. Since this is an endothermic reaction, heat was absorbed by the chemical reaction in order to break down the bonds between the molecules. This resulted in a cold feeling, and this is an endothermic reaction because the heat used to break the bonds released less heat than was used to break.
This is our raw data collected. We conducted 3 DOEs in total, and we used the averages of these 3 DOEs for our data analysis to determine a more common result. This is the effect of temperature. The effect of temperature was found by taking the high averages and subtracting the low averages, resulting in an effect of negative 3.7 degrees Celsius. This is the effect shown on a graph.
This is the effect of mass, which is found in the same way by subtracting the low average from the high average, resulting in an effect of negative 0.2. This is the result shown on a line graph. This is the effect of molarity, which was found in the same way as both of the other effects, by subtracting the low average from the high average. This one resulting in an effect of negative 1.2, and this is the effect of molarity displayed on a line graph.
This is the interaction of temperature and mass. The interaction effect was found by subtracting the slope of the solid segment from the slope of the dotted segment. The slope of the solid segment is mass when it was held high, and the dotted is mass when it was held low. The interaction effect was negative 0.6, and this is shown on the graph. This is the interaction of temperature and molarity. It was found the same way, and the interaction effect was also negative 0.6.
This is the interaction of molarity and mass. The solid segment represents when mass was held high, and the dye segment is when mass was held low. The interaction is found the same way as the previous two interaction effects, resulting in an effect value of -0.3. This is our dot plot of effects. These fences are found by taking the range of standards and doubling it, which were placed at -2 and 2. Since temperature is the only value found outside of this range of standards, it is deemed statistically significant.
Some possible errors of our experiment were that the calorimeter was not an isolated system, which is ideal when measuring temperature change. Because our calorimeter both released matter and energy, it was deemed an open system, which is not as valid as an isolated or enclosed system. Another possible error is that the starting temperatures of the acetic acid may not have been consistent because they had to be transported from both the incubator, fume hood, and refrigerator.
In conclusion, we ended up accepting the hypothesis that the high triazole had the greatest temperature change. Only temperature was deemed a statistically significant factor, which makes sense for our experiment due to the first law of thermodynamics and solubility. Since the acetic acid was at a higher temperature, the molecules were moving faster, which allowed more reactions to occur between the sodium bicarbonate, thus requiring the system to take in more energy from the surroundings, resulting in a colder feeling overall.
Some possible further research would be looking into the bond enthalpies between the molecules and using water and ammonium chloride instead of baking soda and sodium bicarbonate and acetic acid, because water and ammonium chloride are actually used in cold packs, and we only use sodium bicarbonate and acetic acid to mimic these cold packs. To recap, we accepted the hypothesis that the three highest values would produce the greatest temperature change. Temperature was only statistically significant, as Josh explained.
This is our works cited. Questions?
You said that the on slide 19 something about like the starting temperature might not have been the same. If we're looking at the net change in temperature, why would they have to start at the same temperature?
The starting temperature was one of our effects, so the starting temperature of acetic acid had to be at a consistent high, standard, and low value. If they were skewed more towards the standard value, that could have affected how the effect played out and really truly affected the outcome of our experiment.
So let's just say on a molecular level, all right, I wanted it to be at 37 and it was really at 34. What would you expect the result of that? How would you expect the result of that experiment to be different than if it was at 37?
If it was at 37, we probably would have had a colder reaction because the molecules would have been moving faster because the molecules move faster at higher temperatures. Since it's at a lower temperature at 34, they would not have been moving as fast, therefore not as many reactions would have been occurring within the overall reaction, therefore the cold pack would not feel as cold.
What is the chemical reaction?
Sodium bicarbonate and acetic acid. It
What is
produces,
it? Do you have it somewhere? Can you tell me what it is?
it produces sodium
Do you
and,
have the actual?
I have, not in the PowerPoint, but it showed the, bonds breaking and the molecular structure.
So it's in the time it takes in heat. Why does it feel heat? Why does it feel like it's taking in energy? Why does it feel cold?
It feels cold because bonds release energy, but it takes more energy to break the bonds than is